Hello, my name is Koen Verhaege. I'm from Sofics. My presentation is entitled FinFET and FDSOI Solutions for ESD and Analog I/Os. First of all, an introduction on Sofics. Sofics is an IP provider focusing on-chip ESD solutions. We want to offer you higher performance in normal operation, enable applications in harsher environments, and provide a first-time right solution using smaller silicon area. More than 100 licensees worldwide are using this technology, resulting in, on average, one IC release per day for mass production using what I'm going to talk about today. At this moment in time, about 4,500 ICs have been released using Sofics solutions. I will talk about FinFET technology, 60 nanometer down to 5 nanometer, and FDSOI, 22 nanometer. And I'll present you the challenges, the solutions, and I will support that with data. The application challenges. We face the need for very high speed interfaces in FinFET and FDSOI. It basically requires that the capacitive load that is added parasitically to the signal path by the ESD structure should be in the femtofarad range. We also want to build solutions for over voltage or high voltage tolerant I/Os, basically meaning 3.3 volt, 2.5 volt, 1.8 volt interfaces, typically using lower voltage transistors. Also, we face the requirement of low power and low leakage, basically translating to ESD devices that we should offer a solution with picoampere leakage or less. The technology challenges are depicted here. What we see is that for decreasing technology nodes, the supply voltage has ever been decreasing, but also what has been decreasing is the thin gate oxide breakdown voltage, which is the red curve over here. The distance between those two curves is the ESD design window, which is the normal operating area for an ESD protection device, and it becomes smaller and smaller. In, for instance, 0.8 volt FDSOI in FinFET, we typically have a remaining design window of 3 volts only. This is made harder, again, by another technology trend that for smaller technology nodes, the thickness of the first metal layers is thinner and thinner, resulting in a higher resistance. So for the same ESD current and a higher resistance, the voltage window is more consumed. How can we further visualize that? On the right-hand side, we see a typical schematic of what we call dual diode ESD protection. It's very popular. Basically, it uses a diode to divert the stress from the signal line up or from the signal line down to the supply lines. And further, it relies on a power clamp which is dedicated between the upper and the lower supply line. The ESD current is diverted from the sensitive node through a diode, metal resistance, power clamp, metal resistance, and out of the chip, with already knowing that those metal resistances are higher and the intrinsic sensitivity of these sensitive nodes is higher. Basically, we're having a much thinner gate oxides here. This leads obviously to an increased transient voltage sensitivity during ESD. The total stress path is the voltage drop across the diode, the two metal resistances, and the power clamp. In many cases, for the most advanced nodes with the most sensitive applications, also in terms of the signal and the signal load, here in terms of capacitance and leakage, but also the intrinsic sensitivity of the node, we need to seek different strategies with very low dynamic resistive clamps, because there's not only resistance in the metal, there's also resistance in whatever these clamps are here and the power clamp as well. Added to that is that when we look at the MOS solutions in those FinFET and FDSOI technologies, we basically must conclude that they cannot adequately self-protect. which means that a self-protecting driver is not really a good option. And also building ESD protection that extensively rely on MOS transistors in that classic snapback mode is also not a good idea. For FinFET technology, I'm showing you here an example, a TLP curves that is nicely showing the performance under ESD, and right at the moment where a very big MOS transistor is going into snapback, basically we have a damage point, basically disqualifying this transistor as an ESD protection or self-protective device. For FDSOI on the right hand side, the red curve here is a PMOS device, and those other three curves actually are NMOS devices. At first sight, one would think this is something reasonable to work with. However, when we look at the leakage evolution, we see a different story. First of all, it may not be very visible, but we're basically talking about microamperes of leakage, which is very high for an ESD protection device. And in addition, when we look at the NMOS devices, we see this disturbing trend here, that leakage is gradually increasing in the very low stress levels. Now, obviously, at the higher levels, something more dramatic happens, and this is definitely very hard physical damage. But here, this seems to be also a problem, and it should be a reason of concern, and that's why we like to disqualify that type of devices that exhibit that type of behavior. It's just not very reliable to work with those. So what do we need in terms of strategy? We need bidirectional clamps or local clamps that are obviously very small in area, otherwise it's not economically feasible to use them on multiple IOs. Obviously, the same terms apply in terms of low on resistance or dynamic resistance, very low capacitance, and very low leakage contribution to the signal node over here. And for the power clamps, they're also necessary, obviously, because stress between the power lines should also be handled, and obviously also using the very lowest on resistance that is possible. Now, since we're not going to try to replace every ESD device in every circuit, and it's also not necessary because there's many standard applications where the PDK solutions are perfectly okay, we seek for solutions that are PDK complementary. That is very important. When we're looking at the Sofics solutions in general, we're looking at a portfolio that is mostly SCR based. Not all, but mostly SCR based. SCR stands for silicon controlled rectifiers. In a simplified way, it's a PNP connected with an NPN transistor that can discuss the operation. But we're not talking about plain vanilla SCR devices that just merely follow that very simple schematic. What is needed is a lot of techniques that can be applied to different nodes in this equivalent circuit to create an effective ESD protection device. We have this SCR-based clamp portfolio used across a very wide range of technology nodes, and we specifically adapted the designs and the layouts for SOI and FinFET. The end result is here on the right-hand side. We have DRC clean devices that are fast triggering, provide low leakage, are latch-up safe, are PDK compatible, and also very important, do not require any process change. This is a standard process design compatible solution. So let's show you some data. First of all, I'll demonstrate the basic robustness that is available. Then I'll benchmark the leakage of Sofics versus PDK devices, and also offer you a CDM performance assessment. Let's have a first look at some data. This is a FinFET structure, 1.8 volt. It's a clamp that can be used for both power lines and local protection. I'm showing you classic TLP, 1 amp of performance. Very important, the leakage level, 400 picoamps. The area, also very important, very small, 625 square micrometers. And scalable performance. Basically demonstrating to you we can build good ESD protection in FinFET technology. FDSOI technology, I add some more data. Here I'm not only showing you the classic TLP curve, which is the green curve here. It represents what the performance would be under a human body model, and also the CDM performance level, the very fast TLP, which is a 5 nanosecond TLP pulse. Performance, 2 kilovolt human body model, 200 volt CDM, basically the clamp capability for CDM in a 1500 square millimeter BGA package. Two very important features here. The leakage. 20 picoamps at room temperature, 10 nanoamps at 125 degrees C. And an area that is very, very small, 715 square micrometers. I'm also showing you here what the core damage is for the thin gate oxide transistor, that if you're applying it for that particular situation, the performance is not limited by the actual failure current of the TLP curves, but the limit here where there's a crossover into the danger zone, the so-called core damage zone. Benchmarking leakage. On the left-hand side, I'm showing you data for 25 degrees C room temperature. On the right-hand side, elevated 125 degrees C. I'm showing you results for 3 different FinFET processes. I'm showing you leakage. Leakage that is normalized. Normalized for FinFET process 2 and the Sofics protection device for low voltage domain. So this is value 1 and this is also value 1. We have the results for both the low voltage domain and high voltage domain. And in order to make a fair comparison, we've always looked at a 2 kilovolt clamp, one designed according to the Sofics design guidelines, and the other one according to the PDK. What you can see is for all situations, all nodes, and both a low voltage and high voltage, that there is a distance of about 2 to 3 orders of magnitude between the Sofics solutions and the fair comparison to the PDK solution, both at room temperature and high temperatures. Let's have a look at FDSOI benchmarking for leakage. Again, showing you room temperature versus elevated temperature. I'm showing you the absolute leakage in this case, picoamp level, nanoamp, and microamp range. Let's particularly focus in on the blue curve versus the red curve. They are representing blue curve, the PDK solution for 0.8 volts, and the red curve, the Sofics solution for 0.8 volts. What you can see is over the whole signal range and the relevant point of the supply voltage that there is a difference of 3 orders of magnitude in leakage between the PDK device and the Sofics device. Now that I have talked about the robustness and the leakage, let's have a look at the CDM assessment. This is TLP and VFTLP data for FinFET technologies, all domains. So I'm showing you the results for 0.8, 1.8, and 3.3 volts. The thicker lines are the classic TLP curves. The thinner lines are the VFTLP curves. Their leakage evolution is shown here on the right side. All of these curves show you a performance of 3000 volts HBM, more than 250 volts CDM capability in a 1500 square millimeter BGA package, and those results are very scalable. So we have very good confidence that we can use these devices for very adequate CDM protection, as is actually proven by actual products in volume production. Same picture here for FDSOI. Again, 3 different voltage domains, the VFTLP curves, the TLP curves. They're closely overlaying, all of them demonstrating 2.5 kilovolt HBM and 200 volt CDM. Again, that's capability in a 1500 square millimeter BGA package. Scalable performance. What I'm showing you next is a little bit more detail. I'm going to FinFET data again, 5 nanosecond VFTLP. You see the classic curve as I've shown you before, but now I'm going to show you a little bit more data. Actually, I'm showing you the current transient versus time and the voltage transient versus time. If we look at the different points in the VFTLP curve, here the red point is prior to triggering, the light blue is right after triggering. Then we have a data point at 2.5 amps and a data point at 4.5 amps. The current transients are the square pulses that are the input of the test, and you can see them here. What is interesting to see here is the voltage response. The voltage response that you are, by the way, seeing in this curve over here comes out of the averaging out of the tail of the voltage transient. There is more information here in the initial transient or the triggering situation. You can actually see that from the red curve to the light blue curve, before and after triggering, that there is less than a 1 nanosecond window where the clamp is triggered without any overshoot. And then for the higher current stress levels, that you can actually see some overshoot in a very short window of time. That is not problematic. Actually, as it is tested with a parallel gate oxide, we have experimental proof that it's non-problematic. But it shows, and it's a very important curve to look at, that the overshoot in terms of voltage versus time is really limited and that the triggering happens very, very fast. In the next slide, I'm going to show you again another type of data now for FDSOI. And basically what I've done in the next slide is I'm not only showing you this classic VFTLP, but I'm basically also going to plot the peak current that you can see instead of the average current that we extract from the curve over here. We can also draw the peak current in a curve. And this is how it looks. Now we're looking at FDSOI clamp. And here I've compared a standard SCR, which are the green curves, and an enhanced SCR. I've alluded before that it is very important to use proper techniques to make these viable ESD protection devices. And what you can see here is demonstrated that is necessary. The dotted lines are the peak currents. So remember the transient voltage that I showed you on the previous slide. If you not use the average of the tail, but you're using the peak current, you have a shifted curve, which is obvious. Here in the blue curve, the enhanced SCR, you see the proper and desired response. With a standard SCR not having the proper techniques introduced, we see a more problematic, or actually a problematic situation where there is a huge overshoot and real concern for the ability to protect ESD or sensitive nodes during ESD. As a conclusion, I would like to summarize what I've talked to you about. We've talked about the intrinsic challenges of deep nano FDSOI and FinFET technologies, basically addressing the narrow design windows that limits the ESD protection options. I've also demonstrated with data that there is IP available for all interfaces and supply lines that are silicon proven and have scalable performance, that can support your high-speed digital or high-frequency analog designs. I've also demonstrated low-power, low-leakage solutions, 2 to 3 orders of magnitude improvement over the PDK, and this over the full temperature range that we have for our devices. Finally, we have standard process compatible solutions, DRC clean, latch-up safe, and CDM robust. A final overview: the solutions that are offered and are in existence for FinFETs and FDSOI include power clamps and local clamps. But in addition to the PDKs that also include the dual diode and power clamp solution, the Sofics portfolio offers you solutions for semi-local and full local protection, for secondary protection or full local protection plus the secondary protection. In terms of I/O coverage, obviously also the PDK offers and covers the standard I/O ESD solutions. With the Sofics portfolio, we add to that over and under voltage tolerance solutions. enable IOs with core transistors, and also provide the very low leakage and very low capacitance solutions. Thank you very much for listening to me. If you want to have further information, you can contact Urt Houwman, who's our local contact, or myself, the presenter, Koen Verhaege. You can find more information on our website, www.sofics.com, or you can scan one of the three QR codes here and see very short 40-second videos summarizing some of the key benefits of the Sofics solutions. Thank you very much for your attention, and have a nice day.